Hello, my name is Pakornwoon Watanakun. Today I'm going to present about the singing ruler. The singing ruler is IYPT 2026, problem 13. It states that when a ruler is clamped at one end and struck, it oscillates and emits a characteristic sound. Investigate how the sound depends on relevant parameters. So the objective is to find out what factors affect the sound of a singing ruler and experiment to find out how it is related. There are three words that might be misunderstood. First, clamped, oscillate, and sounds. The meaning can be seen as shown in the screen. Now, for the presentation, we're going to be dividing the presentation into three parts: the theory, the experiment, and the conclusion. As you can see, the experiment are divided into two parts. With the experiment 1, we're going to change the ruler's overhang length, and experiment 2, we're going to change the material of the ruler. Now, to derive the theory, we're going to use the Euler-Bernoulli's beam theory. The conditions of a Euler-Bernoulli's beam can be seen as shown in the screen. We're going to model our ruler as a cantilever beam, being freed at one end and fixed at one end. This is a small deflection of the cantilever beam with no shear. So we start off with the Euler-Bernoulli's beam equation, balancing bending moment and inertia. Next, we apply the harmonic oscillator equation to separate the displacement. Now note that there are constant values, so we define those as k to the power of 4 to get a fourth order differentiation equation with the general solution as shown in the red box. Now we can apply the boundary conditions of a cantilever beam from x is equal to 0 to x is equal to L. The fixed end where x is equal to 0, there are no displacement and the slope is 0. The freed end where x is equal to L, the bending moment is 0 and the shear is 0. And we solve to get cos KL times cos KL is equal to -1. We plot that onto a graph and we find out that KL determines mode, and we define that as beta n for every n mode. The first mode has a value of 1.875, which we're going to use today. Now, to derive the natural frequency of the vibrating beam, we use k to the power of 4 is equal to rho a times omega squared over EI, and k is equal to beta over L to get the natural frequency as shown in the red box. Now we're going to use the first mode with the value 1.875 as shown here. There are only one node at the fixed end. Now, to approximate the value for our vibrating ruler, recall that I is equal to BH cubed over 12 and A is equal to BH. So we get the formula as shown in the red box. Now we can find out how the parameters relate to the natural frequency, like so. Now we're going to experiment. The setup are shown right here. We have a phone for voice recording, we have a camera, and we're going to use two softwares to analyze our sound, Audacity and Sonic Visualizer. For experiment 1, we're going to vary the overhang. And so we plot it onto a graph and we find out that it can be linearly fitted to get an equation like this. Now onto experiment 2, changing material. As you can see, we have two rulers with different materials. The ruler 1 has a material that is more rigid than the ruler 2. So we find out the frequency, and we see that as the more rigid ruler tends to have a higher frequency. So to conclude, the frequency of the ruler depends on both the length of the ruler from the table and the material of the ruler. The longer the length of the ruler, the lower the frequency, and the more rigid the ruler, the higher the frequency of the sound, and the ruler follows the equation as shown in the screen. Thank you.